So this is the section that deals with geometric sequences. The only reason that we did the review yesterday was just to get you back in the swing of sequences. It was to get you ready for today. So geometric sequence is a sequence that moves from term to term through multiplication or its equivalent inverse, division. So an example of this might be something as simple as 2, 4, 8, 16. What's happening here is we're multiplying by a common ratio, we call R, of 2. That's what we're doing. Geometric series, oh, and by the way, there's more to these notes. Every geometric sequence can be expressed with the formula, and this is the explicit form. Should I even want to find these yet? Let me scan through these notes. Nah, too early. Then we have what's called an geometric series, which is just a sum of a geometric sequence. And so it might be something like 1 plus a half plus a quarter plus ... And that is a geometric sequence here because the ratio was 1/2. We were cutting the numbers in half as we moved from left to right. Some important things to note here because, it's hard enough for some kids with arithmetic, but the ratio can be found by taking the second term and dividing it by the first. By taking the second, putting it over the first. And you need to check and make sure that that's true because that should also equal the third term divided by the second. Some kids just have to push a lot more buttons than others. All right, find the first 5 terms of the sequence, determine if it is arithmetic or geometric. Hopefully you realize that the first sequence is arithmetic. It looks like mx plus b, but I know your attention span. But anyways, it's good practice. We'll find the first term by plugging in a 1. We'll get an 8 back. 3 times 1 plus 5 is 8. We'll find the second term by plugging in a 2. 3 times 2 add 5 will be 11. We'll find the third term by plugging in a 3. 3 times 3 is 9. If you add 5, you get 14. And we'll find the fourth term by plugging in a 4. 3 times 4 add 5 is 17. And we'll find the fifth term by plugging in a 5. 3 times 5 plus 5 is 20. So what's going on here with these guys is we have a common difference of 3. We're adding 3. So this is arithmetic. We have a common difference of 3. All right, the second one, we'll plug in numbers. We'll just create a list of terms, then we'll decide. We'll see. The first term is 3 to the first plus 5, which is 8. The second term is 3 to the second plus 5. Now 3 squared is 9. 9 plus 5 is 14. The third term is 3 cubed plus 5. 3 cubed is 27. Add 5, you're sitting at 32. The fourth term is going to be 3 to the fourth plus 5, which is 86. And the fifth term is 3 to the fifth plus 5, which is 249. 248. Yeah. So are these geometric? I don't think so, but let's see here. We got 14 divided by 8. I would have a ratio of 1.75. See if it holds. I think it's about to break. 32 over 14 is a ratio of roughly 2.29. So there is no common ratio, not geometric, not arithmetic. This one be neither. It is neither arithmetic nor is it geometric. All right, let's take a look at this one. This one stands a pretty good chance. And there's a relationship between these two things. We are told to find the first 5 terms. So we plug in a 1. You know, 1 minus 1 is 0. And not every one of my Algebra 2 students knows this, but 4 to the 0 is 1. So this is 4 times 1, which is 4. Plug in a 2, we'll have 4 times 4 to the first, which is 16. Plug in a 3, we'll have 4 times 4 to the second, because 3 minus 1 is 2. And we're going to have 64. Plug in a 4, we're going to have 4 times 4 to the third, and we're going to have 256. And plug in a 5, we're going to have 4 times 4 to the fourth, which is 1,024. So is this geometric? Well, let's see. I'm pretty sure it is, because if I take 16 and divide it by 4, I get 4. If I take 64 and divide it by 16, guess what I get? I get 4. If I take 256 and divide it by 64, it happens again. And if I take 1,024 and I divide it by 256, I get 4. So this is geometric. We have a common ratio, which we call R, equal to 4. All right. Part 4. The first term is 4 to the first. Whoops, I don't know why I put it as a subscript, which is 4. The second term is 4 to the second, which is 16. The third term is 4 cubed, which is 64. The fourth term is 4 to the fourth, which is 256. And the fifth term is 4 to the fifth, which is 1,024. See, these were actually the same exact problem. But anyways, this is also geometric. Now let me tell you why these were the same problem. This is 4 to the first times 4 to the n minus 1. We have a property of mathematics, says x to the a times x to the b is x to the ab. If things are alike, we can add exponents. So this is 4 to the n minus 1 plus 1, which is just 4 to the n. Manipulation of exponents, kids. Love it. All right, here's your explicit rules for a geometric sequence. Your explicit form, which is the one that we use most often, says that the nth term is going to be the first term a sub 1 times the ratio raised to the n minus 1. A sub 1 is, as always, the first term. R is the common ratio. On certain things, this might be equivalent to something else. Then you have the recursive rule. That'll be your piecewise function. It'll have 2 pieces. The nth term is the first term if n is 1. And if n is not 1, it is the previous term, a sub n minus 1, times the ratio r if n is greater than 1, because we multiply by a common ratio called r. Just about halfway through your notes. Write the recursive and explicit rule for the following sequences. Write the explicit rule 2 different ways if you can. That's the big thing. All right, so we're going to see, and you're told that these are, well, actually you're not told they're geometric, but I know that if I take 12 and divide it by 4, I get 3. If I take 36 and divide it by 12, I get 3. So this is definitely it's a geometric sequence. So let's start with the rule here. The nth, I'm going to do the explicit first. The nth term is the first term times the ratio raised to the n minus 1. So the first term is 4, and this should say if possible, okay? First term is 4, the ratio is 3, and it's raised to the n minus 1. Now, I can't do the same trick that I did last time because the bases don't match. So that's where this stops. 4 and 3 are not the same. I can't do what I did last time. I do need a recursive rule. This, by the way, was the explicit. The recursive, till I'm wore out, is the first term of 4 if n is 1. Otherwise, it is the previous term times 4 if n is greater than 1. All right, now we have 2, 4, 8. My ratio will be 4 over 2, which is 2. And I'm doing this, and some of you at home are like, why, Milbrath, are you wasting your time? Because not everybody that I teach knows that 4 over 2 is 2. Yeah, that's a true statement. 8 over 4 is also 2. I have a common ratio. So, because I have a common ratio, I'm geometric. The nth term is the first term, which is 2, times the ratio, which is 2, raised to the n minus 1. Now, this one is doable. Or, because these guys are the same, I can think about adding exponents. I can do things like that because those are the same. So let that sink in, all right? Let's do our recursive, and this again was the explicit, which is my favorite form. I talk explicitly too. Recursive form. The nth term is the first term, which is a 2, if n is equal to 1, or it's the previous term times 2. I like to write them like this. Twice a sub n minus 1, if n is bigger than 1. And there you go. 5 9s down on our notes. Bob, the incredible shrinking man, loses half his height every 10 years. Bob's height peaked when he was 16 at 6'4". He's about to turn 26. Stinks for Bob, right? Write out the first 5 terms of Bob's declining height. So 6'4", we're going to do this, and we're going to unify the units here. In inches, 6 times 12 is 72, plus 4 is 76 inches. So he's 76 inches. This was when he was 16. It gets cut in half. Half of 76 should be 38. All right. It gets cut in half again. Now he's down to 19. It gets cut in half again. He's 8.5 inches tall. And he gets cut in half again, and he's 4.25 inches tall. Now, the ratio here was not a whole number. It was a half. We were literally cutting Bob's height in half. Write a geometric rule. All you got to do is know a formula. Could have sworn I say change to orange. The nth term is the first term times the ratio raised to the n minus 1. So the first term is 76 inches. The ratio is a half. The exponent is n minus 1. Can you write that thing 2 ways? No. You can't, because the bases aren't the same. All right, sum of a geometric series. This guy is given to you from Gauss again. I'm not going to explore this one. The sum of n terms is the first term times 1 minus r to the n sitting over 1 minus r. Take that thing, place it right next to your heart, and memorize it for all eternity. All right? You should be familiar with things. N is the number of terms. R is the common ratio. And of course, a sub 1 is not steak sauce. It is the first term that you care about. All right? All right, find the sum of the first 10 terms of geometric sequence 1, 2, 4. As small as this sequence is, I would just write the whole thing out. But you can use a formula too. It's really up to you. But the next guy is 8, followed by a 16, followed by a 32, followed by a 64, followed by 128, followed by 256, followed by 512, followed by 1024. And let's count 1, 2, 3, 4, 5, 6. Where am I at? There's 5, 6, 7, 8, 9, 10. Didn't need that 1024. All right. Now let's use a... And then you know what? I didn't even need this. This was pointless. This was pointless. Didn't need it. Not thinking. Your formula for the sum of n terms, because this is geometric, is the first term times 1 minus r to the n over 1 minus r. See, the arithmetic formulas we were using yesterday required you to know the last term for summation. These do not, because it's easy to predict what the last term is because of the ratio. All right, so we're going to find the sum of 10 things, n is 10. The first thing is a 1. We have 1 minus r, which was 2. We doubled. We're going to raise it to the 10th power, and it's sitting over 1 minus 2. Nobody's asking you to do this all by hand. You can do some of it by hand if you want, but nobody's asking it of you. That's the reality of it. You want to be safe, go to math, num, n over d. I'm not even going to worry about the 1. The top is 1 minus 2 to the 10th. And that's sitting pretty over 1 minus 2. And there you go, it's 1023. If you've got an older calculator, make sure you kind of type it the way I wrote it. There's a reason I write things the way I do. Be careful about this. This needs to be in its own set of parentheses. Wrapping is important. 1023. If you're Dalton D is scanning through the notes, maybe you should start listening, slowing down. How many terms will it take for the geometric sequence defined by a sub n is 2 times 3 to the n minus 1 to have a sum of 59,048? So because this is in the correct form, I already have everything I need. I know that the first term is a 2. I know the ratio is a 3. So I'm going to write down my little summation formula, and I'm going to see what I can fill in. I can actually fill in a whole bunch of stuff. Because I have the ability to comprehend what I read, unlike some of my students, you guys need to start reading more stuff. I can put a 59,048 there. I can put a 2 in for a sub 1. The ratio is 3, so everywhere I see an r, I'm a 3. And that's what I have. And then I can start doing some math, kids. 59,048 equals 2. Notice I'm not doing 1 minus 3 here because this 3 has an exponent, but I can down low. That's a negative 2. 2 over a negative 2 reduces down to a negative 1. I'm playing the isolation game. I want you to pay attention to that. I'm going to divide out the negativity. Negative 59,048 is 1 minus 3 to the n. I also dropped the need for parentheses. We'll go ahead and we'll subtract 1. We'll get negative 59,049 being equal to 3 to the n. Oh, negative 3 to the n. I was getting thrown off there. Anyways, we're going to divide out that negativity, and now we have the positive n. So now I need to figure out what power of 3 creates 59,049. And there's a lot of ways to solve this. The easiest way to do it is to use logarithms. Base, argument, exponent. A log, base, I don't know why I wrote that as an argument. Base, exponent, argument. A log base 3 that contains 59,049, which we can push buttons on a calculator, is equal to n. All right, so let's do change of base here. I like ln. The ln of 59,049, sitting pretty over the ln of 3, is going to be my n value. See, you just thought we were done with logarithms. You just thought that, didn't you? You're never done with logarithms. You're never done with factoring. Sucks to be you. I'm kidding. I love logarithms. You should too. Anywho, push some buttons. A 10. It was 10. You did all that work for 10. Nice. N is 10. All right. I'm not going to lie. I didn't even realize I was going to do logarithms when I saw this problem. Didn't even occur to me. Surprise. All right, so that's what that's going to be. I've got to fill your U-tries out, but that's the notes for this section. We'll work on this in class Friday, I think.